Welcome to the Crazy Hat Chemist. So another video here on periodic trends. Bam! Today we're going to be talking about successive ionization energies. Ionization energy, IE. Okay, these ionization energies that are here are in kilojoules per mole, and they correlate with the valence electrons and the group number. So, if you look on the very top of this graphic here, I have the elements written down as far as their symbol, like Na for sodium, Mg for magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. On the vertical axis are ionization energy 1, ionization energy 2, 3, 4, 5, 6, and 7. Respectively. So, if you take a look at sodium, sodium is in group 1. So, how many valence electrons in sodium? 1 valence electron in sodium. So, to remove the first electron, which is an ionization energy, removing an electron from the gaseous state, to remove that first electron costs 496 kilojoules per mole. That's not very much. Now, there are no more valence electrons. The remaining electrons are core electrons. So the next electron to be removed, that is the second ionization energy, there's an enormous jump here, and that is 4,562 kilojoules per mole. So you should see that removing a valence electron is very easy. Core electrons are nearly impossible to do. So let's take a look at the next one here, which is magnesium. Magnesium is in group 2, an alkaline earth metal. And so since it's in group 2, it has 2 valence electrons. So removing the first valence electron, which is the first ionization energy, costs 738 kilojoules per mole. Okay, now I have a magnesium of a 1+ charge. Now, magnesium is in group 2. There are 2 valence electrons, so magnesium will lose a second electron, and that's the second ionization energy. That second electron costs 1,451 kilojoules per mole. So notice that there is actually almost a doubling, if not more, of the cost per electron when it's from the first to the second of the ionization energies for magnesium. This is due to the fact that you're going to have an increased positive charge. That's the effective nuclear charge in the nucleus is greater. There's less electron-electron repulsion within that same orbital, as well as one of those electrons has been removed. So that's why it costs more money or more energy, effectively, to remove that second electron than the first. However, once you have a magnesium that's a 2+ charge, now you have you have removed both valence electrons and you have only core electrons remaining. So to remove the third electron is a great dip in energy to remove that one, and that's 7,733 kilojoules per mole. That's effectively not going to happen either. Let's look at one more here, and that is aluminum. Aluminum is in group 13 or 3A, and therefore it has 3 valence electrons in it. Okay, and removing the first valence electron, that is the first ionization energy, costs 578 kilojoules per mole. That's not very much. Okay, now you have an aluminum ion that's a 1+ charge. To remove the second valence electron costs 1,817 kilojoules per mole. Significantly higher than the first. That is because it's a 3s2 3p1. That 3p1 was the first one. Okay, and then that second now a valence electron, which is the second ionization energy, costs quite a bit of energy to remove at the 1,800 kilojoules per mole. However, there's still one more valence electron to remove, and that third valence electron, by removing that one, costs 2,745 kilojoules per mole. Now you have aluminum as the predicted charge that it would have, which would be a 3+ charge for an aluminum ion. Okay? To remove any other further electrons would be dipping into the core electrons, and that costs a tremendous amount of energy, and that's why there's that giant gap there of 11,575 kilojoules per mole. And that is effectively not going to happen. You don't find aluminum ion as a 4+ charge. You only find aluminum ion as a 3+ charge. So you should look at the rest of these, and you should see that this yellow staircase line corresponds to the group number of which it's in, and the number of valence electrons which would be removed effectively. Argon already has an outermost shell, and that's why it's 1520 kilojoules per mole to remove the outer electron on argon. So that's effectively not going to happen. Chlorine also has a high ionization energy as well because it's a non-metal. Non-metals don't like to lose electrons, and therefore they like to gain electrons instead. So that's why those values are already high as well. Okay? I hope you enjoyed that video, and I got another crazy hat for you, and bam! From World War I. Give me a thumbs up if you like that video, subscribe to my YouTube channel, and I will see you next time. Cheerio now. Bye.